smaller than the distance. For k, it's less clear, but it's hidden in very short notes of radial elliptic. The difference, if you think that H is the global entropy and K is the entropy which comes from almost every leaf, so the difference between the two is also fundamental. Is the entropy which remains in the, I mean, it's another entropy. And maybe, I mean, the entropy of the reverse process or something. But it's an entropy, so it's non-negative. And now, for that, once I fix the measure, I can write formula. I can apply Ito's formula, and I can, there are many ways of computing. That's what we did in the negative curvature case, of computing these numbers. And you see why now Ln is smaller than Km, with the equality of the F and the everywhere, but just coefficients inequality. Two, the one for the L2 integral and the one for the scalar product. Because the gradient of C is 1. And finally, there exists some harmonic measure with Ln equal to L. So, and the harmonic measure is unique. So I know that Ln is equal to L. So L square is Ln square. Ln square is smaller than Kn, and Kn is smaller than H. So if I have equality, I have equality also in the middle term. So I have equality here. So I have. I think it's the last. Yeah, it's the last slide.
Thank you. We'll do this. And the dynamics, and usually you characterize the dynamics possessing the shelving property. And from time to time, I back to the expansive system. Today's main my talk is about a major expansive system. But just before, please give me 15 or 20 minutes, and let me describe my a little bit on the shelving property, and please understand my split. Usually I direct to. Okay, let's start. So. Let it be across infinity manifold, and usually denote the diff of M, the set of all diffeomorphisms of F of M denote with a sequence topology. You know the notion of pseudo-orbit very often appears in several branches of dynamical theory of dynamical system. So, for instance, if you study dynamical system in numerical way, then the calculated orbit are the so-called pseudo-orbit. The pseudo-orbit is something like this. Let F be R diffeomorphism, and sequence of points in here. Okay. So this is so-called the delta pseudo-orbit. Delta pseudo-orbit. The sort of sequence is called epsilon shelling by point Y. At Y, to Y, something like that. And within, when this distance is within zero, then at this point, this trajectory, this orbit is called epsilon shelling orbit. Shadow. Denote by, okay, let me give a more precise definition. F sharing property. This is the abbreviation, if and only if for any epsilon there is delta, so that for any delta pseudo-orbit, for any delta pseudo-orbit can be epsilon shadow by some point. So let me denote by the S of M, the set of all diffeomorphism with shading property. And denote this one, let me consider the interior of S of M. Of course, the interior is implied with respect to the C1 topology. I mean, F is in interior of S of M. If and not if every C1 nearby system of F also has the shading property. This means interior. So,
what is the topology of the diffeomorphism?
C1 topology. It is well known that F is structurally stable if and only if this is by Manier. I'm sorry. Maybe it's 86 or so by Manier. Axiom A. A strong transversality combination. And more formal results are obtained. If F satisfied action A strong transversality, then F has I'm sorry. Okay. Interior S of M. Any element this is in the this property implies the shadowing property. This set is constructed of open set. The F is in the interior. This is by Lobis. Maybe 1970s around that. My result is this in 1994. In this proof, the main thing to prove is two things. Main things to prove we have to any periodic point hyperbolic and the stable manifold and I'm sorry. Stable manifold and unstable manifold are all transverse. So, let me describe the outline of the proof 1 and 2, and then I hope you understand my what I'd like to do. I mean, so the by contradiction. The support they exist are periodic point. In this outline, we only the case, we consider only the case, the fixed point. And there exists eigenvalue lambda of if the differential equal to 1. Equal to 1. We suppose that this is non-hyperbolic. And next, we consider this type of map. And we perturb the diffeomorphism F in the small neighborhood of P. And we construct something like nearby system. D or small neighborhood of P. The serial small number. Then we see that this such a kind of diffeomorphism D is super nearby. I mean, G has the sharding property. But the sharding property is continuously invariant, resolved by the conjugacy. This is just continuous. So, I mean, df also has the sharding property. Okay. Really recall that the differential, this one is the, again, we consider the simplest case, two-dimensional case. So this is the P, and this is the Argentinian space corresponding to the lambda. And in this outline, we assume that the normal direction is expanding. And another case is the argument is all the same. Okay, so the act this rank. Remember this map has the sharding property. So we fix this point, for example, A and B, and we construct the pseudo orbit. Oh, I'm sorry. And the restriction is identity map. Okay, so first we assume that P is non-hyperbolic. Okay, so we construct the pseudo orbit from A endpoint A to B, going forth and back, something like this. X0, X1. Just equally divide. Just equally divide the length delta. Okay, so something like x01 xn, and going forward and back, and this point, something like, and go back. And equal to n. I don't know, something like. So this is the delta pseudo orbit of this map. Okay. So going forward and back infinitely many times. Okay. So this map must have the sharding property, but unfortunately, such a kind of pseudo orbit cannot be epsilon shadowed. You can see the normal direction. Normal direction is something. So if there exists a sharding point here, oh, I'm sorry, sharding point here, then the four orbit divergence. Okay, so cannot shadow this part. And if the sharding point is on this line, then do not move. Okay. So anyway, such a kind of pseudo orbit cannot be shadowed. So any periodic points are hyperbolic under this assumption. Okay. Number two, let's see. please turn on number 2. Number 2 is the transfers. We by contradiction, in this case, we consider such a case, more simplest case. We have tendency P and equal to Q and O are fixed point. Fixed point. Okay, and periodic points are of course hyperbolic. Then we have the tangency point here. By contradiction, they exist. We assume that there exists a tangency point here. Then we perturb this map, something like this. We attach here. Okay. This is perturbed map. Of course, such a kind of perturbation is C1 small. So G also has the sharding property. Okay, so let me construct a pseudo-orbit for G. This is, in fact, is OX. But this one is x minus 1, and also x minus 2, and 3, and something like that. The backward, this are a backward orbit from here, something. And for positive orbit, we consider this one. This is, of course, Z. And jump, one jump here, one jump here. Jump. Okay. One jump. And then consider the forward orbit of this point. Let me name this one x2, x3. This is a true orbit. Okay. This is the orbit. But unfortunately, this kind of pseudo orbit cannot be shadowed of any point. In fact, there exists assume there exists a sharding point here, very nearby. I mean, there's something like this, and then why? The point what must be in this front part, because this is a hyperbolic fixed point. So this kind of argument, x, y, p implies y is okay. So the negative part of all alone within epsilon, then since P is hyperbolic, y must be in the local unstable manifold. Okay. So this point y must be in the unstable manifold. And the point is very nearby x0, so y is in this front part. Please imagine please iterate this part by this map. Then y orbit get to there. We cannot follow this part. Cannot shadow this part. Okay. So if f is in the interior of the shadowing diffeomorphism, then must be transposed. Okay. So in this talk, I'd like to explain the similar, in some sense, similar problem for expansive system. In the same spirit. So let me start here. The major expansive diffeomorphism. Of course, its expansive system is also value of what appears in several branches of modern theory of dynamical system. You know, the expansivity plays an usually important role in the stability theory, and not only so the major expansive diffeomorphism. As I explained, as you know, the results and techniques is developed in solution of stability conjecture and non-uniformly helpful theory of dynamics. Let me already introduced the manifold diffeomorphisms. Space of diffeomorphisms with certain topology. This is distance with epsilon closed ball. Usual lambda denote the closed invariant set of F. The periodic points, this is a period, and this is the wandering set of F. Please recall, we said that F is expansive with expansive constant C. The two orbits are all alone within C, then the points are coincide. In other words, if the distance point they exist, and such that this distance greater than C. Okay. So this is a space of Born probability measures with weak topology. This is the invariant one. This is our ergodic one. Of course, these sets are getting smaller and smaller. We say that the mu is atomic. They exist point mass is positive. These are sets of all atomic measures. This set is you see this set is an intersection of the usual stable set and the unstable set. Also, this set is well-known target of the entropy expansive definition of entropy expansive. We say that the entropy expansive. This the entropy of this set is usually 0. Now, let me introduce the major expansive. Let mu be given. We say that F is major or mu expansive if there exists delta, for any delta, for any x, the major is equal to 0. Maybe this definition is, of course, introduced from the viewpoint of the Measure-theoretic, viewpoint. So it is very natural to consider such a kind of definition. Actually, this definition and these definitions are equal. I mean, for almost all x. Let me remark that if mu is non-atomic and F in itself expansive, then F is mu expansive. This is by definition. Example. Let me recall the dental map. transitive diffeomorphism with rational potential number. Then it is known that there exists a control set with this property and uniquely got. The more is true that this map is expansive. The expansive system is expansivity is first introduced by Woods in 1950. At that time, the main problem of expansive theory is which space can admit the expansive system. He proved that there are no expansive systems, homomorphisms on the unit itself.
Did you go back to the definition of the expansive?
Okay. I'm sorry.
So what you measure for new expansive, you want it to be globally supported. Should it be globally supported? Should every set have open set have positive relations?
No. Just
Yeah,
okay.
Basically, if mu is ergodic, right, it's quite easy for it to be expansive, no?
This one?
No, in general,
Oh.
if you have an ergodic measure,
No.
Just take the irrational rotation.
Ah, yes.
no, but mu expansive. If you look at the definition of mu expansive,
The irrational.
Irrational rotation is
That's
also
forward impact. Forward impact. Small
yeah.
The measure is positive. Irrational.
I think mixing with it. Mixing.
Thank you. Let me go. Okay, so another presentation. So PE, these are set of all diffeomorphisms. Set of all diffeomorphisms. This set, the set of all diffeomorphisms F, such that for any mu, just a probability measure, mu expansive. For any mu, F is mu expansive. And this one is diffeomorphism on F, such that for any mu, any invariant measure, mu expansive. For any invariant measure, this F is mu expansive for any mu invariant measure. For any mu invariant. This set is the set of all diffeomorphisms for the mu expansive for any ergodic measure. We just say EM is the set of all diffeomorphisms expansive. Actually, is expansive. So you know that the major set are getting smaller and smaller. So the underlying dynamical system getting larger and larger. Okay. So I mean, I'm sorry. I mean this problem. So please recall this one. Every expansive diffeomorphism, if mu is non-atomic, then F is mu expansive.
What is the difference between I, and E?
Oh, this one?
Yes.
Oh, this one is ergodic one.
Aren't they the same? Or you're going to if it's 0 for every ergodic,
Yes.
then it's 0
But
invariant. Probably.
But Okay, there are difference. We have so kind of difference. So measure is maybe this is a set of diffeomorphisms.
I mean, so it's just a thing of measures. The measure of
If the diffeomorphism
Technically, if you have somehow a continuum of periodic points, maybe those are different ones.
Okay. Thank you. Okay. Okay, so let's go forward. Let me explain the Kazuhiro system. Kazuhiro system. This system is we say that the diffeomorphism F is Kazuhiro. The non-zero vector must be bounded, unbounded. I mean, the iteration of this set is bounded, then V must be zero. We say that this system, Kazuhiro. It is known that also this result is by Manier, and F is in the interior of expansive diffeomorphism. Whose interior? If and only if the F satisfies both axiom, and this is so-called the Kessler transversal intersection problem. Intersection problem. We have 18 minutes. Okay, let me, maybe it is not so easy to imagine such kind of system. Let me explain shortly. Example. At first, so the 2111, this is two-dimensional, okay? Then the FA is the usual analysis induced from this matrix. And let me recall the Euclidean space of this system is something like this. And we perturb this one is such a way. What I explained is a dA with small fluctuations, or we can construct two diffeomorphisms with one source and sink. This is called dA. Derived from the NASA. Of course, this example is two-dimensional. In two-dimensional case, any Kazuhiro system must be a NASA. So this is not the example of the Kazuhiro system. Just please remember. Okay. So next, we construct three-dimensional dA. Three-dimensional dA. This is the n-unstable space. This is one-dimensional stable space on three-dimensional torus. Okay. So we perturb this one something like this. Also, the dA. I mean, one source and two saddles. One source and saddles. And this is also saddles. Okay. And this is three-dimensional. dA of the three-dimensional torus. Let me call this map G. And unfortunately, it is not so easy to draw a three-dimensional torus. Let me, instead of this, two-dimensional. So there exists a source. There exists one-dimensional Ergodic set. Index 1, I mean the state dimension index 1. And also, we construct that this is a G. And another three-dimensional torus. We consider G inverse here. G inverse here. So there exists a Ergodic set, and this is a sink. But, you know, the stable manifold, unstable manifold is one dimension. Oh? I'm sorry. Source. Stable manifold is one dimension. Oh, okay, it's okay. The stable manifold. One dimensional, something like this line. And this one is n-state manifold is one dimensional. Oh, I'm sorry. Something. And we consider a connected sum of these two maps. Something. Okay. So we twist some part, and we then as stable manifold and n-state manifold intersect something like that. Just one point. Okay. This is our example of case analysis. This type of diffeomorphism is in the interior of the expansive diffeomorphism. This is the set of all diffeomorphisms of new expansive for any invariant measures. And we consider the C1 interior. Before that, let us record some basic known fact. This one is just one point. This set is the intersection of the stable set and then stable set. Only one, just one point. There are no other point here. It is very well known for any invariant measure. The measure of the invariant wandering set is equal to 1. The axiom A, therefore, axiom A implies F is expansive for any invariant measure that is not an atomic. And also, if we assume the additional non-cycle condition, then F is omega stable. So this assumption, any nearby system also will expansive. Yes. Let me equal this one. Set of all diffeomorphism that is new expansive for any invariant measure. We have this one. If is in the interior, if and only if the F satisfies axiom A and not cycle. As we see, the if part is already checked. What we'd like to do is, if is in this interior, then satisfies axiom A. To do, we use this well-known important fact. This result is by Hayashi. If one of them is every nearby system, all a periodic point of every nearby system is also hyperbolic. F1 of them. So this is not I'm trying to just principle the belief part. Suppose that there exists periodic point with an eigenvalue equal to 1. I assume the non-hyperbolic. Then it is easy to construct the expansive measure, inverse measure. It's very easy. Let me see. In fact, this is a small arc. I mean, please remember in my first talk, in the blackboard, I consider the eigenspace with respect to lambda equal to 1. And this is a small piece centered at P. I mean, we have such a equality. Of course, we have to exponential match. I'm sure. Okay. So let LP be normalized living measurement on LP, just the length. So let's define as usual way. We take average. Then it is easy to see that this set has a positive because this map is identity map on LP. This implies that if it's not expansive, this is a basic idea. Okay. Okay. So we have the interior of the ID is equal to the actual man and also omega stable system. And let us recall the PE. This is just a measure expansive for any measure, probability measure. For any probability measure. So the set is more smaller than IE. Please recall that this interior of this set is actually, interior of this set is mega stable. More smaller set. What is that? This set is equal to coincide the inertial system, just expansive system. Okay. Okay. One more, with more. 7 minutes or something like that. Let me explain the EE formula. This type of splitting is called dominant splitting. Let me see. Uniform contracting, uniform expanding, as usual. Partially we say that the lambda is partially hyperbolic. There exist three direction, the invariant splitting, such that the this one and this one are both dominated splitting, and the right hand side and the left hand side are uniformly expanding and contracting. Please let me introduce the set. The Lobastry non-hyperbolic transit. Lobastry non-hyperbolic transit. The Lobastry means itself is already open set. I mean, there exists C1 neighborhood of that. That any G, the element is non-hyperbolic and transit. The Manier constructed the open set Lobastry non-hyperbolic transit system on three-dimensional torus. This is open set such that any element has a partially hyperbolic. The central direction is integrable, and this is a leaf is for any max the homomorphic to dr. There exists a delta such that our set main target is contained in C of X. Okay, and this is what I've drawn. This is the set of our target. Okay, so Well, of course, everywhere. If this open set is not expansive. Not expansive. So, let me go forward. Recall that EE, the set of all diffeomorphisms that mu expansive for any ergodic measure. For any ergodic measure, F is mu expansive, so that for any ergodic measure. So we have the manias of the set is contained in EE of three-dimensional torus. If it intersects Kripke's merit, then contained in the IE of T3. Okay, let me explain the triangle quickly. Triangle, this one. So please recall this is the O is the opposite. Each element has a such product. This is a set or target. It's contained in. So what I'd like to do is the measure of the gamma delta x is equal to 0 for any ergodic measure. Oh, okay, this one. For any ergodic measure. Case one, this leaf is individual. And it is easy to see that this leaf is invariant, and measure is also invariant. So this means this measure is equal to 0. And this is very easy. In this case, it's very simple. There's case 2. They are periodic in some sense. Then we assume that this leaf is equal to the homomorphic to R1. So if necessary, twice of F to N, then we may assume that our orientation is 0. So then the non-wandering set is contained in the fixed point set. We see from this, we see that this one. In fact, we consider such a kind of set. This is well known that since mu is ergodic, such a set, the measure of such set is equal to 1. So we take this one. Assume. Okay. So by contradiction, we suppose that. So this set has intersection by measuring mu. Then take this one. Then we see this is a fixed point set. The z is in fact a periodic point. So this limit converges to this one with topology. Moreover, by choice of z, this limit must be mu. The mu must be this type of periodic measure. This is contradiction. Mu must be in non-atomic. This is so we have such a equality. It is easy to see that in this one. This measure is equal to 1. Okay, so we have another generic result. The GEE is set of all diffeomorphisms. They exist residual set in the ergodic measures, such that for any mu F is mu expansive. Then this set is residual in the set of all diffeomorphisms F and okay. That's all. Questions, remarks, please?
I want to have my problem.
Thank you.
If you want to eat, then only 2 minutes break.
I don't want to drink.